First two questions for warm-up, between 0 and 2 pi. What do you have to do first for the first one? We're going to first have to get sine by itself, right? And then you're going to have to do the inverse. So there is a little start for you. And that finds your reference angle. When finding your reference angle, okay, the step in between here, even though sine of theta is negative 2/3, when you're finding your reference angle, you always need to do the inverse of the positive value. Because if you actually drew the triangle, you would draw a triangle with the opposite side with a length of 2 and a hypotenuse with a length of 3. So your reference angle is always the inverse of that positive value. So if you get a reference angle of 0.73, which quadrants is it going to be in? Quadrant 3 and quadrant 4. So you're going to have to go pi plus this reference angle in quadrant 3 and 2 pi minus that reference angle in quadrant 4. I'll put that answer up in a bit. If you've got them already, start B. Okay, how did you do? Did you find these two answers? This time it was 2 decimal places. It's fine. Part B. Have you got your reference angle already for part B? Yes? You want to check if you got your reference angle correct? Quadrants, which ones? A tan is negative, so it'll be quadrants 2 and 4. Two more questions, so you still have room in the column of page 572. For C, these are non-calculator questions. And in D, we're going to introduce all the solutions. So that theta belongs to all real numbers right at the end of D. That's meaning the domain is everything. So in that one, we're going to start introducing all answers. Can someone tell me why C is non-calculator? Because when you solved it and got cos theta by itself, you get a value that is not on your unit circle.
Because it's x over r, so it's 4 over 1.
Right? You get 4, right? And 4 over 1 is bad because it's bigger than 1, which means that it's not possible. So whenever sine or cos are bigger than 1, if you think that cos is adjacent over hypotenuse, and so if we think of this as a fraction, 4 over 1, that would mean my adjacent side, if I tried to draw this triangle, would be 4, and my hypotenuse would be 1. And you can see why that's wrong. Right? Your hypotenuse is always your longest value. So anytime that you have sine or cos bigger than 1, if you tried to draw that triangle, it would be impossible. So these become non-calculator questions because you're expected to be able to recognize that that's not possible. Now for the last one that we're doing in this section, tan of theta, root 3 tan theta plus 1 equals 0. And the reason I chose this was for a couple of reasons. First of all, when you solve for tan of theta, you get negative 1 over root 3. And this is the first place where you might run into a problem because we didn't write this value on our unit circle. But if you rationalize this, 1 over root 3 is the same as root 3 over 3. So whereas you don't need to rationalize your final answers, you have to be able to know how to do that because you might not recognize 1 over root 3. as being the same as root 3 over 3. And root 3 over 3 is on our unit circle. What family for 10 gives us root 3 over 3? Pi over 6 family. What quadrants will it be in? 2 and 4. So if we were solving this like normal, which would just be once around the circle, you would write down the pi over 6 family member in quadrant 2 and the pi over 6 family member in quadrant 4. So 5 pi over 6 and 11 pi over 6, and you would be done. But since this question said we want all answers, well, basically, here's 5 pi over 6 on our unit circle. It could also be a negative angle that ends there. You could also go around one full time and end there. You could go around twice and end there. Anything that's coterminal or ends in the same place as 5 pi over 6 will give us a tan value of negative root 3 over 3. So we need to write these two answers and everything that's coterminal with them. Now the notation that we're going to use is going to look like this. A little bit similar to what we've seen before. We take 5 pi over 6, which is one of our answers, and we add 2 times pi times k, right? This is how we wrote it in the past. Generally, I don't know why, the 2 gets written first, the k gets put in the middle, and the pi gets written at the end. It wouldn't be bad if you wrote 2 pi k instead of 2k pi. They're the same thing. But what they're saying is we can go around the circle, full revolution of 2 pi, as many times as we want, where k is an integer. So this is this part at the end here, the kez. That means k belongs to all integers, meaning all positive and negative whole numbers. So you're adding and subtracting multiples of 2 pi. We don't have a closing bracket. And the same thing with 11 pi over 6. Add 2k pi to that as well. So this is saying that in our diagram here, we've got 5 pi over 6 and 11 pi over 6. And you can go around the circle and hit it as many times as you wanted. Right. So this is a right answer. But what Peter's mentioning is if I start here, right, and what this plus 2k pi says is go around once, stop here again, go around again, stop again, go around again, stop again, go around again, stop again, over and over and over again. And what Peter is noticing, he says, if I started here and went halfway around the circle, I'd get here. And half again, I'd get back here, and half again, I'd get back here. Could I write something that shows that instead? And yes, you can, and it is a little bit more elegant. So you could say, I'll start at 5 pi over 6, and I'll just add k pi, which is halfway around the circle, as many times as possible. And this is a more elegant answer, but it only works with tan. Like for sine and cos, you would have to go back to adding 2k pi. And for many of you, you'll just add the 2k pi because it's easier. If I find my answers between 0 and 2 pi, and then just write the coterminal ones with those, then I'll get the general solution.